In our last video, we looked at the basic ways in which we can transform a sine function and the associated equations. In this video, we're going to extend further by combining several transformations into the one equation and then using that equation to sketch the graph. Any trigonometric function can be expressed in terms of its general form. The following are the general forms for the sine, cosine, and tangent functions. Each of the variables A, N, alpha, and C represent different features of the trigonometric function. For example, the variable A in each of these expressions represents the amplitude, that is the vertical distance between the highest point or the lowest point and the center line. Next, the variable N represents the angular frequency. The angular frequency tells us the speed of rotation, and it is related to the period, which is how long it takes to complete a cycle, by the equation t is equal to 2 pi divided by n. Next, the variable alpha represents the horizontal phase shift. This tells us how much the graph shifts horizontally from its usual position. And lastly, the variable c represents the vertical shift. This tells us how much the graph shifts vertically from its usual position. We're now going to work through some examples on how to graph trigonometric functions by using information from the equation. Our first example is y is equal to 2 sine x plus 1. From this equation, we can extract information such as the amplitude, angular frequency, horizontal shift, and vertical shift. The amplitude is given by the number 2, which is the number in front of sine x. The angular frequency is the coefficient of x, which in this case is just 1. In this example, we don't have a horizontal shift, but we do have a vertical shift of +1, which means that the whole graph will move up by 1 unit. So here's the graph of y is equal to 2 sine x plus 1. The red dotted graph is the original graph of y is equal to sine x, and the blue graph is the transform function y is equal to 2 sine x plus 1. So we can see that the center of motion has moved up by 1 unit. The amplitude has also changed from 1 to 2 units. The period is unchanged since the angular frequency is 1. This means that we're able to complete one cycle within 360 degrees. Our next example is y is equal to 2 cos x divided by 2. This equation can be rewritten as y is equal to 2 cos half times x. We can extract information about features of the graph from the equation. The amplitude is given by the number in front of the cosine function, which is 2. The angular frequency is given by the coefficient of x, which is 1/2. There is no horizontal shift in this equation, nor is there a vertical shift. And here's the graph of the transform function. The red graph is original function y is equal to cos x, and the blue graph is a transform function y is equal to 2 cos x divided by 2. Note here that the amplitude has changed from 1 to 2. The angular frequency is 1/2, which means that we can only complete half a cycle within 360 degrees. So if we want to complete a whole cycle, it would take 720 degrees. Our third example is y is equal to -1/2 sine 2x minus 2. In this example, there is a negative sign in front of the sine function. This means that the original sine x graph is reflected about the x-axis. The amplitude is given by the number in front of the sine function, which is 1/2. The angular frequency is given by the coefficient of x, which is 2. There is no horizontal shift in this example, but we do have a vertical shift of -2. So here's the graph of the transform function. The red graph is y is equal to sine x, the original graph, and the blue graph is the transform function y is equal to -1/2 sine 2x minus 2. You can see that in this graph, the original graph has been reflected about the x-axis, It has also been shifted down by 2 units. The amplitude has reduced from 1 to just a half. Since the angular frequency is 2, this means that we're able to complete 2 cycles within 360 degrees. Our last example is y is equal to 2 sine 2x minus 60 degrees minus 1. Our first step is to express this in general form as y is equal to 2 sine, then we're going to factorize out the 2. So that we've got 2 times x minus 30 degrees inside the bracket, and all of these subtract 1. The reason we want to do this is because we want to make sure that we have got the correct value for our horizontal phase shift. So from this equation, we can now deduce that the amplitude is given by the number in front of the sine function, which is 2. The angular frequency is also 2. We have a horizontal phase shift of 30 degrees to the right and a vertical shift of 1 unit downwards. So here's the graph of the transform function. The red graph is the original graph y is equal to sine x, and the blue graph is the transformed function y is equal to 2 sine 2x minus 60 degrees minus 1. So from the original graph and the transformed graph, we can see that the center of motion has gone down by 1 unit. There is also a horizontal shift by 30 degrees to the right. The amplitude has also changed from 1 unit to 2 units. And if we look at the angular frequency of 2 means that we're able to complete 2 cycles within 360 degrees. And because we're starting at 30 degrees, adding 360 to that, that's going to be 390 degrees. So starting from 30 degrees, that's our first cycle. And this is our second cycle. Thanks everyone for watching the video. I hope you guys found it useful. For more videos on this topic or other topics, please have a look at our channel. If you haven't already, don't forget to subscribe. We release videos weekly across various maths topics, and we would love to see you guys all in the next one. Bye for now.